Hello all, welcome to this tutorial in which we will be completing one derivation that was left in our discussion in the class, which is for ordinary least square, and then we will be solving a couple of numerical problems from MLE estimate, map estimates. That is the agenda for this particular tutorial. Without any further delay, let's jump in. So, we are looking at the ordinary least square solution. Now, here, the idea is our function that we have, the isomorphic function that we have is theta transpose x. I'm considering here an augmented data. Now, when I mean by augmented data, that means that if data belongs to RD, I have increased it by one dimension by putting 1 there, and then in theta, I have put the bias. Okay. So now x belongs to RD plus 1, and theta belongs to RD plus 1. This is one instance of x. So now, if I have n examples, my overall x that is there now will be the first example, the second example, so on like xn. Okay. Now I have n rows, I have d plus 1 columns. So now my x matrix which is there is n cross d plus 1, and the y that I have y1, y2, so on till yn, which is n cross 1. Okay, now I am assuming that the output is a scalar. So now, when I go ahead and assume that, so we are looking at ERM with linear model and squared error loss. This is the consideration. Then the overall problem. Now obtaining the optimal parameters, theta star is argmin of theta 1 over n x theta minus y, the second norm of it. Okay, now this is the whole thing. So I'm considering all the data points together. Therefore, I'm not considering this I is equal to 1 to n. Since I'm considering all the points, the output of this will be a vector. This is a vector. So you can take each one of them, and then if you take it, it will finally boils down to the same equation that we had earlier. So now we can take this and expand. So I just want to know, when I have this second norm as y transpose, okay, and this is nothing but this. Okay, so now this will be x theta transpose x theta minus x theta transpose y minus y transpose x theta plus y transpose y. Now let's look at this. And this should be a scalar. Okay, this is a vector. Now this is the dot product. So this is a scalar. Vector transpose into a vector. No, this is dot product again. Again this is dot product. Now all of them are scalars. Okay. Therefore, the overall outcome will be a scalar. Okay. So now this will be, this I can write it as y transpose y plus x theta transpose theta minus 2 into theta transpose x transpose y. Okay, now these are same actually, so twice of that you can do it. Now this is your equation. So now how do you find the argmin? Now the idea is quite simple. Now you just differentiate with respect to theta. Okay, now again this is a scalar and theta is a vector. Okay, now you are taking the partial derivative of a scalar. Okay, no, the final outcome will be a scalar is what I mean by that with respect to a vector. Okay, so now it will be, now I have to take the partial derivative with respect to, this is independent of theta, so therefore this will be 0. So now taking the partial derivative with respect to 2 theta transpose x transpose y, now this will be 2 into x transpose y. Okay, so now again we need to take a dot product between 2 into x transpose, oh sorry for that, now this is theta transpose x transpose x theta. I want to take the partial derivative of this, then this will be 2 into x transpose x theta. So now whenever you are taking a gradient, now the gradient will also be of the same dimension as that of theta. Now what is the dimension? Oh sorry for that, so yeah, yes, it's correct, sorry, it will be of the same dimension as that of theta. So now this is a d cross 1 into d cross 1 matrix that you are multiplying it by d cross 1. So therefore this whole thing will be a d cross 1. The same thing will apply for this. Okay, now this is d cross 1 into n that you are multiplying by a vector of n. So n cross 1 to be more specific. So you get, sorry, d plus 1 cross 1. Okay, d plus 1 cross 1, you will get it, which is as the same dimension as that of the theta. Okay, so now just put all of them together. Now therefore you differentiate with respect to theta and equate it to 0. Now differentiate with respect to theta and equating to 0, we will get minus 2x transpose y plus 2 into x transpose x theta. Now this implies x transpose x theta equals x transpose y. Now assuming that now this is a matrix. Okay, now assuming that the inverse exists, theta equals x transpose x whole inverse x transpose y. This is the optimal value of theta. Now I will leave a couple of things here. Now one is, now what if there is no inverse? Now then comes the idea of pseudo inverse. I'm leaving that for you to look into. So that is one specific thing. And then the way in which we proceed in obtaining the optimal value for theta star now will be same for even for generalized least square solution. Okay, now there what will happen is you have to take it into the consideration of the transformed space. Okay, you are not dealing here in the transformed space. Okay, now there you have to deal with the transformed space, but the overall idea will be similar. Okay, this is now with respect to the ordinary least square solution. Okay, now this is much, if you have studied linear algebra as a course, I would have seen similar kind of what do you call solutions. Okay, so So let's go to the next problem. Now the plan is we'll be solving couple of problems on the risk, and then on the MLE estimate, and then on the map estimate. Okay, these problems are the credits should go to Professor P.S. Shastri, sir. Okay, in while he was teaching the course in our institute. Now these questions were curated. I'm using couple of questions from them. So it has nothing to do with these numbers. So these numbers are just some numbering that was there earlier. Okay, I'm just reusing these questions. So the main idea of all these questions is to give you an intuitive feel of how things work. Given a problem, how do you go and work? Okay, so now let's take a. So we are saying that we are taking a two-class pattern recognition problem, now two-class classification problem with feature vectors in R2. Now that means that you have your points in R2. Okay, so now we can easily plot R2. So now let's plot them first. Okay, so now is the question then says that the class conditional densities of class 1 is uniform over 1, 3. Now this is x1, this is x2. Now when he's saying that it is over 1, 3, so now it is. So let's point them up. Okay. This is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay. So now over 1, 3. That is, this is 1, 1, 3. Okay. This is one class. Okay. The points are uniform from this. This is class 1. Okay. Now the class conditional for 1 is uniform over 1, 3. And for the class 2, it is uniform over 2, 4. Okay. So then for the another class, it is uniform over 2, 4. Okay. This is the second class. So now, suppose the prior probabilities are equal and you're using 0, 1 loss. Now we have seen all these things. Now consider the line x plus y equals to 0. Okay. So let's consider that line x plus y is equal to 0. So x is 0, which makes, this makes y is 0. This is 5, 5. Now a line joining these 2 points is the one that consider. Okay, now this is the line. This is the line x plus y equals to 5, or x plus x1. Okay, better way of saying is so x1 plus x2 equals to 5. Okay, the reason why I'm not using y is in our connotations. Normally we have y as the label. Okay, so therefore I'm not using it. So suppose we consider x plus y in R2. Is this a base classifier for this problem? And then he's saying that is the base classifier unique for this problem? If not, can we specify 2 different base classifiers? Okay. So this is the first part, and then we will change the class conditional densities, and then we will go ahead. Now we will come back to the remaining part of the question. So now let's resolve. Let's look at this problem. So I assume that all of you are clear with this representation. Now your class 1 is from this, your class 2 is from this. You have an overlap, now that is there, and then this is the line that you are saying. Now what do you mean by that? Anything above this belongs to class 2, anything below this belongs to class 1. Okay, so now that is the idea. So now let's put things up. Now the probability, the priors, y is equal to 1 equals y is equal to 2 is half. Okay, and then we are using 0 1 loss. Now what do you mean by that? Whenever the classification is proper, so the loss incurred is 0, and whenever there is a misclassification, the incurred loss is 1. Okay, so now we know that. So whenever you have a base classifier with 0 1 loss, okay, now whenever you have a classifier with 0 1 loss and then you're considering the base classifier, so now it will boil down to comparing the posteriors. Okay, now whichever posterior is higher, you will be putting into that particular class. Now base classifier with 0 1 loss, so now is comparing posteriors p of y is equal to I given x. Now, this is what you will be actually comparing. Now how will be the rule? The rule will be, so if y is equal to 2 given x is greater than y is equal to 1 given x, then you'll be labeling that particular example. You'll be having y is equal to 2. Now otherwise you will be having y is equal to 1. Now, this is our uh, base classifier. Okay, so now then it boils down to, now we know that y given x by Bayes rule, you know that it is x given y into probability of y divided by probability of x. Okay, now this is there. Okay, since we have equal priors, now comparison of posteriors can be looked into as comparison of just class conditionals. Okay, since priors are equal, probability x y is equal to 2 greater than is equal to 1, then you say y is equal to 2. Okay, now this is your classifier. Okay, so now let's bring in a couple of things. Okay, so now we know that x given y is equal to 1, this class conditional is uniform over the region 1 comma 3 cross 1 comma 3. Okay, let's call this region as S1 pertaining to class 1. The area of S1 equals to 4. Okay, so and then how will be our class conditional density? 1 equals 1 over 4 for x belongs to S1, 0 otherwise. Okay, so now whenever the x that you are choosing, now please remember that whenever I say x is in a point in R2. Okay, here x belongs to R2. Okay, whenever you choose a point in R2 and then that belongs to this region S1, now then the class conditional density for that will be 1 4. Now that means that you choose any point from this. Okay, now it has a probability x given y is equal to 1 is 1/4, and any point apart from that it will be 0, even outside of this. Okay, so now similarly let's look it for the other class also. Now probability that x given y is equal to 2 is uniform 2 comma 4 over the region 2 comma 4 2 comma 4. Okay, now let's call this region as S2, and we know that the area of S2 is 4. Okay, so and then probability that x given y is equal to 2 for any given x. Should have specified here x. See, I'm sorry, I'm abusing a lot of notations. Now, I assume that all of you are able to recognize these abuses. Okay, this is 1 over 4 for x belongs to S2, 0 otherwise. Okay, I'm just thinking of a joke. See, now I was a TA for when probability course was happening in institute. I was a TA, and then for these kinds of abuses, I have actually cut marks for people. And there might be some people who might be looking at this, and then he's saying that what is happening. Okay, so but yeah, I'm assuming that all of you are able to recognize the abuses that we are doing. Okay, so now this is one region S1, this is another region S2 that uh, I'm going ahead. So, and then there is a region S1 intersection S2. Okay, now I'll call it as S12. Now, which is 2 comma 3 cross 2 comma 3, and the area of this S3 is 1. Now, speaking of this intersection region which we are looking into. Now here the area is 1. Okay. So now in this particular any point that belongs to S3, what happens is probability that x belongs to y is equal to 1 equals probability that x given y is equal to 2 is 1/4 for them. Okay. Now then what do you do? Now here it's a bit of a tricky task. Okay. So now now this we understood. Okay. So now with all these things in place, now let's proceed. So now the next part of the same question that we are asking is, now we are considering, now consider x1 plus x2 equals to 5. This is the discriminator that you're considering. Now what do you mean by that? Now is x1 plus x2, if it is less than 5, then I am saying that y is equal to 1. If x1 plus x2 is greater than 5, then I am saying that y is equal to 2. What is it equal to 5? We break ties arbitrarily. Okay, so just break ties arbitrarily. Okay, now that means that now whenever any point, okay, that belongs to S2, which is here, now I am saying all these points are belongs to y is equal to 2, and for all these points that are there, I am saying that y is equal to 1. This is what I am saying. Okay, this is one region, this is another region as per the classifier. Okay, so now what happens in this case? Now you have to find the risk. Okay. Now, if you want to say that whether this is a base classifier or not, now we have to find the risk of this. Correct. So now, how do you find the risk of this? The risk of HB is you look it over all the support R2 and min of probability y is equal to 1 and conditional equal to 1. So now this, I can divide the whole thing into multiple regions. Okay. So now let's say that I will have a couple of regions. Region A. Now what is this region A? S1 minus S2. Okay. Region B. That is S2 minus S1. Now what are these regions? Okay. So now this is region A. Now in which you are not considering the common points at all. This is region A. And this is region B. Okay. So now any point so that you are considering here, for any point that you are considering here, okay. For example, let's consider this point. Now probability that x given y is equal to 1 will be 1 by 4. Probability that x given y is equal to 2 will be 0 for this. So whenever you take the risk, you will be considering this, the minimum of them. So you don't need to worry about this. Okay. And whenever you compare them for classifying, now this is higher, you'll be putting it into class 1. So now that means that you don't have any problems with these points being classified. Now these are perfectly classified points as class 1. The same thing holds good even here. These points are perfectly classified as class 2. No problem at all. So for points in region A and B, the risk is actually 0. And since all of them have just outside these two regions, the density is 0, I don't need to even consider that. So considering the overall R2 support which is there. Okay. So now I can divide this whole thing which is there into region A. Okay. So okay, region A, region B, and then there is one more region C, which is S1 intersection S2. Now this is this common region which is there, which is 2, 3. This is the region that I am considering. Now this is where actually the risk needs to be computed. Okay. So now region A now plus, okay, change, plus integral with respect to region B plus integral with respect to region C plus integral outside. Now you can outside. Now this is 0, 0, 0. No need to worry. I just need to worry about this particular thing while computing the risk. Therefore, it is nothing but 2 cross 3 into 2 cross 3. I should be only worried about this region. And what is the value? This is half. This is 1/4. For any point which is in this region, both the class conditional will have the valid value 1/4 by 4. Okay. And therefore, the minimum of them will be 1/8 dx. This will be 1/8. Now the optimal risk that you are having is actually here 1/8. Okay, now please look into this. I haven't even brought in that line at all. Okay. So now, when we say that something is a base classifier, now we know that base classifier is the one that gives you least risk. Now I am able to obtain the risk which is 1/8. So now I need to calculate, now when I have that line, what is the risk involved? Okay. So now that is the next point that is there. Now with respect to this particular discriminator line, for this region in which there is a misclassification that can happen, now compute the risk. Now I presume that it is fairly simple, and then you can see that, okay, Now it is 1 over 8. Okay. Now the main point was computing the risk of this, and then now it is easy to see that. I'll just make that point. So now it is easy to see that the risk involved when we consider the points of S1 intersection S2, it will be 1 over 8. Now how do you compute it? Now risk is nothing but so you are looking at expected loss that is incurred. Now I presume that you will be able to compute it. Now you have the base risk, which is same as the risk that is obtained in this particular case. Okay, so now the next question that immediately arises is, now is this classifier, now the risk is same, now is this classifier that I have, this line, is this a base classifier? Yes. Now because I am able to obtain the least risk. Okay, now is this the only classifier which can give me the same risk? No. Okay, now I can have a classifier for all this region in this. I can say it is y is equal to 1. For all the elements, that also will give me the same risk. For all these things in the region, now there is, I'll say y is equal to 2. Now in both of the cases, I get the same risk. Now therefore, same value for the risk. Now therefore, it is evident that now it is not a unique classifier. Okay, the uniqueness is not there. Let's make that point. Is okay, before that, therefore x1 plus x2 equals to 5 is a base classifier. Okay, now the next point is it a unique base classifier? That means that do you have any other base classifier with same risk? Now no, the answer is no. If I have let's say that I have classifier 1, now decide y is equal to 1 for all x belongs to region 1, 2, then also the risk involved with this particular classifier will be 1/8. Classifier 2, that is decide y is equal to 2 for all x belongs to the intersection region. Now then also now it will be the same value for the risk. Now, therefore, it is evident that now x1 plus x2 is equal to 5. The line that we have considered is a base classifier, but not a unique base classifier. Okay. So let's go back to the question. Is this a base classifier? Yes. Is the base classifier unique for this problem? No. If not, specify two different base classifiers. Done. Now, then we go to the next part. Suppose the class conditional density are changed so that the density of class 1 is still uniform 1, 3, but for class 2 it is 2, 5. Okay, so now that means that there is a change now. Now 2, 5 we are considering. Okay, so now okay. Okay, so now we are comparing this. These are the two densities that you have in hand, the orange and pink. Okay, so now Is the line x plus y a base classifier? Base classifier? No. If not, specify the base classifier. Okay. Is the base classifier unique now? No. If whatever base classifier that you get, is it unique? For the case of class conditional, suppose. Okay. Now we will come there. Now let's find the base classifier for this. Okay. Now this is, I prefer to call it as part 2 of this problem. Okay, now here the class conditional y is equal to 1 is uniform 1 comma 3 cross 1 comma 3, and then it's given y is equal to 2 is uniform 2 comma 5 cross 2 comma 5. Okay. So now let's call this now as the region 1 and region 2, represented by S1 and S2. Okay. So now then what will happen? Now please see that now the area of this region is 9. Okay. Now therefore, x given y is equal to 1 equals 1/4 when x belongs to region 1, 0, otherwise. Okay. And then the class conditional for another class y is equal to 2 equals 1/9 for x belongs to region 2, 0, otherwise. Okay. Now again, now S1 intersection S2 is again the same region, 2 cross 3 cross 2 cross 3. Okay. So now in this case, now what is the question? So now whenever you are using the same line now, for anything here, you decide y is equal to 2, no problem now. Okay. For anything here, you decide y is equal to 1, no problem. No, because the other class conditional will be 0. Now the only issue that arises is in this intersection region where in which both the class conditionals have value. Now in S12 now, x given y is equal to 1 is 1/4 and x given y is equal to 2 is 1/9. So since they have equal priors, so base classifier with 0 1 loss is nothing but comparing the posteriors. Since they have equal priors, it's comparing the class conditionals. Now it is evident that 1/4 is greater than 1/9 implies in the overlap region, I decide y is equal to 1. Okay. In the overlap region, we decide y is equal to 1. Okay. So now the question is, now can I take that x1 plus x2 is equal to 5? Is it base now? No. No, because now what happens is, now we just saw that the optimal base classifier in this overlap region, it has to consider, now all these is one class, this is another class. Now that is what optimal base classifier is for this current class conditional. I repeat, now since in the overlap the class conditional of class 1 is more, the overlap region should be classified as class 1. Okay. Now therefore, when I consider, that is the optimal base classifier. Now when I consider this line, this particular region is considering as class 2, which should not be the case because this is an overlap region. Now in the overlap region, it has to be considered as class 1. Okay, now therefore the line that you are seeing is not a base classifier. Okay. So let's make note of this. The next point is, now Now, now is x1 plus x2 equals to 5, is it Bayes classifier? That is the next question. The answer is no. The reason is because x1 plus x2 greater than 5. So intersection S1 2. Okay. Now we say y is equal to 1 as per Bayes classifier, but when you use the line, using the line, it is y is equal to 2. Okay. Now therefore, x1 plus x2 is equal to 5 is not a Bayes classifier. Now then the Bayes classifier that we are considering, now that is, which is saying that this whole region is class 1 and this whole thing is class 2. Is it unique? Yes. Because there is no overlap. Now since there is no overlap, there is no kind of clash that is happening. So the decision is fixed. Now, therefore, the one that we are considering is a unique classifier in this case. Okay. Now, in this case, the Bayes classifier that we are considering is unique. Why? In the overlap region, there is no tie to break arbitrarily. Therefore, decision is fixed. Therefore, it's unique. Okay. Now this gives us the answer for the second part of the question. Okay. So now let's look at the third part of the question. The third part of the question is for this class conditional identity, suppose that wrongly classifying pattern 1 to pattern 2 is 10 times more expensive than wrongly classifying pattern into class 2. Okay. Now, would it be a Bayes classifier? Is the question. Okay. Is the question fine? So now, when you're classifying any pattern of class 2 to class 1, now that is any in this region or in this overlap region that is there, okay, in this full overlap region, if you are classifying it as class 1, then it is 10 times more expensive. Okay. Now then how do you consider the case? Is a question. Okay. So now let's deal with that. This is the part 3 of our question. This is part 3. Okay. Now that is cost sensitive Bayes classifier. Okay. We are considering the cost sensitive Bayes classifier. Now wrongly classifying the example into y is equal to 1 is 10 times more 10 times more expensive than wrongly classifying y is equal to 2. Then wrongly classifying y is equal to 2. Let's say that y is equal to 1 when truth is the actual label is y is equal to 2 is lambda 1 2, it is 10 times more expensive. Okay, y is equal to 2 when truth is y is equal to 1 is lambda to 1 equals to 1. Now whenever you have correctly classification, the penalty now occurring is 0. Okay, so now what happens is, now it is nothing but the risk involved if we decide y is equal to 1 is 10 times that of the posterior. Then similarly, risk involved if we decide y is equal to 2, then it is 1 into given x. Okay, now then it means that we want to minimize the risk, therefore choose y is equal to 1 if the risk involved in choosing y is equal to 1 is less than this case. Then you choose y is equal to 1. Okay, now since priors are equal, since priors are equal, this can be considered as x given y is equal to 2 is less than x given y is equal to 1. Now this actually I can compute this. This is x given y is equal to 1 divided by x y is equal to 2. This has to be greater than 1. See, now what does this mean? The likelihood that is there of these conditionals, when it is greater than 10, now then you will go ahead and decide it as class 1. Now we know these values, right? Now what are these values? Okay, now these values are, okay, now this is x given y is equal to 1 is 1/4, 10 into x given y is equal to 2 is equal to 10 into 19. This is approximately 1.11. Now this, and we know that this 1.11 is less than one minute. Let's do something. So now then saying that now 1.11 is less than 1/4 is not true. Now that means that in the overlap region, no, you cannot choose y is equal to 1. In the overlap region, actually you have to choose y is equal to 2 now. Now therefore is false, which implies in overlap region, decide y is equal to 2. That's all. You would have been logically, if you have thought of this, yeah, since it is 10 times more, now in the overlap region, what do? You decide that y is equal to 2. Now that means that this whole thing which is there, this whole thing which is there, you see it as y is equal to 2, and only this region which is there, this region which is there, you call it y is equal to 1. Okay. So now what about the base class? This is the base classifier because we have obtained this by now comparing the class conditionals. Okay. So now therefore, finally what does the classifier boils down to? This whole story. Now in S1 minus S2, now we decide y is equal to 1. In S2 minus S1, we decide y is equal to 2. In S12, which is the overlapping region, we decide y is equal to 2 due to high cost of misclassification, high cost of falsely classifying it as y1. Okay, this completes the problem. Okay, now this is how we approach a given problem and then solve them. Okay, so now we will stop this tutorial at this point. Now we have two more problems that are there. Now we will meet at the second part of the same tutorial and then we will continue that. I hope this was useful. Thank you.